Nicolas Dejon. I'm from France, so I'm registered at the University of Lille, and I'm hired by the French national telecom company Orange. And both institutions collaborated during my PhD. And so I'm presenting the one output of my PhD, which is Pip-MPU. And Pip-MPU is the adaptation of the Pip kernel for constrained devices. So first of all, our interest lies in the security of small computer systems. And so the equation is as follows. So we have many cyber attacks and impactful cyber attacks in the recent years, and the risk is even growing further because of the explosion of the IoT market. And these devices have specific characteristics, and they are resource limited. That means that they have a small memory space, limited power, and they have hardware and software computer components that are very heterogeneous and different from general purpose systems. And so we want to secure these constrained devices. So before going further, here are some background details. So I'll speak about an operating system kernel. So everyone knows what's an OS, like Windows, Mac OS, or GNU Linux distributions. And we will define the kernel as the programs that, so the software layer that is the most privileged in a system, so that runs in kernel space, compared to the rest of the OS that could be like file systems that doesn't need this level of privilege, and that is rejected in the user space. So everything else, including applications, are unprivileged. And so typically in a small computer systems, you only have two levels: one privileged kernel space and one unprivileged user space. I also will speak about constrained objects, and constrained objects are defined as compared to their memory size. And so specifically, we focus on devices that are minimum 250 kilobytes of flash until 1 megabytes of flash, and around 50 kilobytes of RAM. So during the PhD and during the work I'm presenting, we worked with these three devices, and as you can see, they are all ARM Cortex-M type, so processor type devices, so of type microcontroller, and this processors have one special unit that is called the memory protection unit, and this one allows to have some access control on specific memory regions that we call MPU regions. So we have one MPU region that has a store address, an end address, and some associated access permissions. And we can compare it with the memory management unit, so that we found in general purpose systems. So that also includes virtual memory, compared to memory protection unit, the MPU, that doesn't have any virtual memory. And also it's much more constrained because we only have like 8 to 16 MPU regions. So on the devices listed here, there are only 8 regions that can be protected at the same time, compared to millions of pages that we can find in an MMU-based systems. So if we could take a look at the state of the art, we found many systems that already use the MPU to secure the devices and secure in a way that they isolate memory spaces. However, when we take a look at the characteristics, we can see that mostly they have an immutable permission models. That means that all the access permissions have been decided before execution time, so at compilation time or even before. And they don't provide any memory extensions, and they also have a very limited flexibility. What is meant here is that they don't provide any nesting of memory spaces, and so they only have one single flat isolation. I put some system into parentheses because either their permission model is mutable, but that is a bad practice because that means that have more privileges to do so, and so that they circumvent their security model. And the memory is either not limited, very limited, of a limited extension, or it's, like I said before, it's using the too much privileges. And we don't want that. We want something that is completely mutable, completely extendable, but secure, with a compartmentalization that is generic. That means that we can either isolate memory spaces, but also their inner functions, and not only one abstraction like the process. And also we want very high flexibility. That means nesting of memory spaces to have many levels of protected subdomains. And so this hasn't been achieved yet, and that's why we created Pip-MPU. So the plan is to first focus on Pip-MPU and then to evaluate the solution to see if it's really usable on constrained devices. So first, Pip-MPU, so as I said, is we merge the concept of Pip, the kernel Pip, and a framework that that has been presented in previous works. And so what we do first is that we list the requirements of Pip, and which has a security policy that we want to keep, but also some naming conventions, because we want a user that is using Pip to use the same abstractions on Pip-MPU. We also need a very high flexibility that is provided by Pip, and reasonable performances because we want it to be usable as an isolation layer for many systems. And specifically also for Pip-MPU, we have another set of requirements because we don't want any hardware modifications, so it can be deployed on many devices immediately. And we also want some real-time consideration, like bounded execution time, also more related to the constrained environments, like a low memory consumption or a low power consumption. And so that means that from the Pip side, we also remove everything that is related to the MMU. So everything that is related to the virtual memory. And there are many structures that we get rid of. And on the other side, we also want to maintain the subspace, the framework space subspace concepts, and so that allows this nesting of subspaces. There is a second step that is to implement the system, and so so we have these three devices that I spoke about earlier, and so we recycle all the Pip's compilation tool chain, and so that we keep the same framework, and port the Pip-MPU to these three devices. About the framework, so I won't speak about it in details, but what's important here is that we have a centralized privileged MPU entity that runs in kernel space, and then all the rest of the system is in user space. That means that here we have some memory space P0, that could be a process, for example, that has a set of memory blocks and that are stored in what is called slots, and all these slots form the metadata structures. So what the framework allows is that this memory space is protected by the MPU at any time. And then we have an interface to create subdomains out of the initial domain. So from P0, we can create P1 and P2. So P1 gets his own memory from P0. And then you can also see the blue arrows. That means that we can cut some memory blocks to fine grain the isolation. And we can do it recursively. So you can see like we have many nested protected memory spaces. And we can see in P11 that it has two metadata structures. Because we can add some new metadata structure, and so that it extends the number of memory blocks per memory space. And so, like I said, we have this interface that allows to share and to retrieve some memory blocks from a subdomain, to add and remove some metadata structures, to cut and merge some memory blocks, and to create and destroy subdomains. And the last service activates it just to have a direct control on the MP. And from Pip side, so we have Pip is specialized in memory isolation, and it only do two things: the memory management and the control flow management. And so, as you can see, we have this also this nested memory space concept in Pip, but it has a strict security policy, and that you can see with the vertical black bars. That means that any subdomain is strictly isolated from each other. And so what we do is that we, this privileged entity from our framework, we use it to replace the MMU entity in Pip, so to specialize the framework and achieve the same security policy with Pip-MPU. And so we did these two steps, and the details are in the paper. And now we want to evaluate the systems. So we want to evaluate it according to three characteristics. So we want to have very high security, very high performances, but also very low memory footprint. So to be run on unconstrained devices. About the test bench, so we have one board which controls another shield that is a power profiler kit that is measuring the energy consumption at any time. And so we have one board that is controlling this power profiler kit, which is mounted on the board where the application run, the test application run. And so we have three scenarios. So first we have the baseline scenario, that is the application that runs in kernel space. That is the most typical scenario in this class of devices. Then the second scenario, that is the application runs in the root partition. And so we have, as we can see here, that Pip is the only one that runs in kernel space. And we have the third scenario, that is that the application runs in the child partition, so a child partition from the root partition, and we have still Pip that is the only one that runs in kernel space. And so we have this purple bar that shows the isolation between the user space and the kernel space. And so for our benchmarking campaign, we have several loops. So we want to configure and compile one scenario, execute it, and then do some analysis to get some report. And so first we run the experiment several times so that we can have an experiment time that is over 20 seconds. We repeat it to have an average and to and calculate the standard deviation to see how it reacts. And then we do this for 4 benchmark applications that is from a standard MBench IoT suite. And finally, we do it for 6 scenarios. So the 3 scenarios that I presented earlier, and the same 3, but with the MPU disabled, that will help us to have an idea of the energy consumption of the MPU. And so the final step is to produce the statistics. And so we have, so this is, for example, the energy consumption. And we have, like we crafted the test to isolate the test phase, that is the red line compared to the rest. In terms of results, so we have Pip-MPU that takes 10 kilobytes from the flash memory. That is about 2% of one of our device. It takes 516 bytes of stack usage. So that's less than 1% of RAM of the same device. And with the metadata structures, I told you we have we can add or remove some metadata structures. So we have a minimum and a maximum per partition. That so we have a usage of around 2% to 7.5% of the RAM of this device. And so we can conclude that if you have a small memory footprint, and this is so percentage are given compared to this device, the DWM1001 dev, which is the smallest that we have. So if we have a bigger system, we have better values. About the performances and the energy consumption, we can observe we have a downgrade of 16 to 18%, which can look enormous, but which is in fact reasonable. First of all, because we can, there are some security benefits behind that I will speak about just after. There are some optimization leads that we are gonna implement, and there is a current port of the operating system Riot that will validate our results. And there is one important fact, that is that the MPU consumption just take a small part of the total energy consumption, and that is again some arguments to not use the MPU. So we are showing that it has a very small incidence. And about the deployment time for a partition, so it's in milliseconds, so it's fast, and so we have reasonable overhead at this stage. We're relating to the security metrics. So we have we can remove 94% to 98% of the accessible memory for partition. So the 1% that is remaining is Pip that is executing, that can't be removed. And about the privilege cycles, so we can so it shows actually that everything is rejected in user space, because this 1% left is again a Pip-MPU that is executing. So we have a very small attack surface, which means a better security. And finally, we didn't retain some other metrics that are used in other benchmarking, security benchmarks, because they are not relevant for our use cases. So the ROP gadgets and indirect calls, we block them with Pip, so that they are not relevant, and the number of them are not relevant either, because we are using functional programming, so we have a lot of gadgets. Data execution prevention and the WXRX principle are local security policies that can be used with Pip-MPU, so there are no means to to calculate it, to compute it. CPU sleep cycles, Pip-MPU is not going to sleep, so we are not calculating them. And there is a distinction between the supervisor calls and the privilege cycles. And in the case of Pip-MPU, because Pip is the only one to run in the kernel space, then it's the same things for us. And for final words, so we are interested in the security of these small constrained devices that are taking a dominant role in our around us, for as well for private, industrial, and strategical interests. And so they are actually the very privileged targets for cyber attackers that can use them for lateral compression, for example. And so in the paper that I presented, we provide some isolation solution to secure these devices that is portable. So between these devices I showed you, but also between different processor versions and even architectures. And it reaches a flexibility level that has never been reached before. And so Pip-MPU is this merge between Pip for constrained devices using the MPU and this specialization of the framework. And it's also the first time that we have an MMU-based system that is transposed to be MPU by keeping also the flexibility and the security. And finally, I also showed you that the evaluation of Pip-MPU showed reasonable overhead for constrained devices. And so we are confident in the port that we are doing right now. So I told you about Riot OS, but we're also considering porting other operating systems so that they can benefit from this isolation layer that is provided by Pip-MPU. Thank you very much for your attention.